Okay. I think that we can start. Before to start with the new presentation on the MPI collectives and communicators, I want to show to see with you the results of some of this exercise. Only the first two or three, in order to see what is the solution. As I told you before, in the first exercise, we have only to extend the Hello World program, including also the total number of CPUs and the ID of the single CPUs. This is the program. As I told before, I have to include the MPI header file. Then I have to do my declaration. I have to initialize the MPI environment, use MPI common size and the MPI common rank in order to know the total number of processor and the ID of the single processor, and then I have to print this information using a printf, and this is quite easy to understand. In the second exercise, it is a little bit more complicated. We have to implement a message passing communication between between two core. Particularly, I have to find the rank of the single core and put this information on a variable, send this variable before from task 0 to task 1, and then and putting it in a new variable named b, and then I have to do the same with task 1, sending the ID of the variable on task 0. At the end, I will have on task 0, on processor 0, 0 as value of A and 1 as value of B. On task 1, I will have 0 as B, 1 as A. Then finally I have to print B for both the two processor, and in this case the solution is this one. As before, I have to include the header file, use common size and common rank to obtain number of processors and the ID of the single processors. Then I have to perform the send receive operation. In this case, for example, for processor 0, I perform before one send and then one receive. For processor 1, in order to avoid the possible deadlock, since I am using the blocking send and receive, I have to write before the receive and then the send. And finally, I have to print the obtained information. I can modify also this code following the suggestion of the text in with this method, in which I'm using the non-blocking send and the receive. In this case, and only in this case, because we have only two processes, we can avoid also the if cycle. In this case, we simple name u, a variable named u, with the label of 1 minus me, where me is the ID of the current processor. So if me is 0, then u will be 1, and if u will be 1, and if me will be 1, u will be 0. So I can use, as I told you before, an non-blocking send and a blocking receive. Using this method, both the process 0 and 1 will arrive here and will send the value of the variable a to the other processor that I named u, and then, since the send operation is non-blocking, both the processor can pass to the receive operation and receive the information. So, using this method, I can avoid some lines of code. And, yes?
What if I also use a non-blocking receive?
It is not necessary, because it is the second operation.
Ah, okay. So at the end, the process...
And then if you use a non-blocking if you want to invert using a non-blocking receive and a blocking send, for example, you can have some problem, because the receive operation could be completed before that the send operation is completed, and in this case you lost your information. Okay, that's it. You will have also other 4 exercises, and I suggest you to do also this exercise, at least at home, if not here. In any case, at the end of the second presentation, we will have probably some time to see also this exercise. In any case, you can send me an email in the next days, and we will reply you if you have some questions. Okay, now I think that we can start with the second presentation. Okay. As I told you before, the second presentation is on MPI collectives and on creation of communicators. Okay, until now we have seen communication point to point, that is from one processor to another one processor. Now we want to see also also the instruction to perform communication between one processor and another group of processors, or between all the processor and each other. for example, I want to share some information and collect a global information, taking information from all the processor, and I can also perform this kind of operation using a standard MPI instruction. Clearly, for collective communication, it is not necessary to define a tag because the communication is collective, so it is not necessary to have a tag that identifies a specific communication between two specific cores. And also the collective communication need to be blocking, and it is impossible to, at least for the standard MPI implementation, to have non-blocking collective. In the MPI 3 standard, also the non-blocking collective was included, but the implementation is currently not complete, and the command that you need to use are more complicated. So at the moment we will stop our course with the standard collective blocking communication. Clearly, if you want to perform collective communication, the buffers in each processor need to be large enough to contain the information, and they have also to match in size. The kind of communication that requires that can be named collective can be divided in synchronization operation, data movement operation. We will see in the next slides what kind of data movement we can do, and global computation instruction. Clearly, the first one kind of collective operation is the MPI barrier command. The syntax is quite simple. It is in C. It is a simple function. In Fortran, clearly the syntax is the same. The only difference is that in Fortran this is a subroutine, and you have also to put here the error variable. But in any case, the MPI barrier command stop all process within the communicator that we use, for example, MPI common word, until all the tasks are synchronized. We can imagine to have, for example, five tasks, and in this case the tasks have different speed. We can imagine these are the tasks, and the barrier starts here and stop all the tasks until this situation is reached. When all the task will arrive to the barrier, and only after that all the tasks will arrive at the barrier, the program can go on. And this is the first synchronization operation. After this, we can see the broadcast operation that could be very useful for you. For example, you can imagine to have some data that was created on processor 0, for example, the master processor that read the data from a file and so on. and you want to share this information with all the other tasks. In this case, you can use the MPI broadcast bcast function to share this information with all the tasks that you have in the communicator. The syntax is quite simple and very similar to the point-to-point instruction. The only difference is clearly that you have not to specify the ID of the receiving task, since you are sending the message to all the tasks you have.
Excuse me, relating to the example that you proposed now, so reading some data from one file from the master process,
yes,
and distributing it among all the processes that I'm planning to use. It is the right approach, this one, so only one process access the I/O device for input and then spreading the data through the interconnect solution that I have, or would it be better to rely on the high performance I/O available to all the processor to get the data directly from the file, for example?
Okay, I can tell that it is the most common approach, but not the most efficient. The most efficient is to use, for example, MPI-I/O in order to read the information and then share the information to the other, the MPI-I/O to read the local information you need, and using the MPI-I/O you haven't any necessity to use the MPI communication to spread the information. Another feasible approach is to without using MPI-I/O, each process read its own file that contains only the information it needs, and this approach is quite common. Another, and probably the most efficient approach, is to use a library to perform this kind of operation. A library like, for example, HDF5 or NetCDF library that are optimized for a lot of parallel machine and can perform this operation for you in the most efficient way. So this is a very short example of the use of the broadcast function. Clear. Also in this case it is written in Fortran, but the syntax in C is very similar. As before, you have to include either file, declare the variables, declare common size and common rank, and then, for example, on the processor 0, I set this variable with the values of 2 and 4. Then, if I want to share this information with other CPUs, I can broadcast the information simply using MPI bcast. The first element is A, the name of the variable, the name of element that are contained in A, the type of the variable, MPI real in this case. Then I have 0, that is the processor that send the information, and the communicator and their variable. Clearly, if I put here 0, 0 will be the processor that send the information, and clearly since I use MPI Common Word, this information will be shared with all the processors that I'm using. Then I can write the variable, and I can see that in all the processors the variable have the same result. Okay. We can also do the inverse operation of broadcast. For example, we can use the gather function, MPI_gather. With this operation, each processor, each course, each task, as you want, root included, send the content of a buffer to the root process, and the root process collect all the information that it receives, maintaining the order of the CPUs. So imagine that this is the information we want to share, and we have 4 processors from 0 to 4, 0, 1, 2, 3. Yeah. This function put the first block at the of processor 0 at the beginning, the second block after the first block. The second block is the block of the second processor. The third block is the block of the third processor, and so on. The syntax also in this case is quite simple. For example, we can I can show you this. This is the syntax. As before in C, this is a function, an integer function. The first argument of the function is the variable. The second is the dimension of the variable we want to send. For example, I want to pass 3 elements for each processor. Then the data type, the received buffer. I can, because in this case I can put all this information on another buffer, but if I want, I can reuse the same buffer. For example, if I can declare A with a dimension of 10, for example, real elements, and then I can pass the first 2 elements for each processor to the same buffer.
So when I specify the same buffer, is up to the MPI implementation, putting the first 2 elements on my root,
yes.
the one of the root processor, and then the other of the other processor.
Yes, clearly you overwrite the first buffer, the buffer of the first processor, but in any case it's feasible. You can put here what you want. The only important thing is that the dimension need to be adequate to contain all the information you send. Then the dimension of the receiver counter, the data type, the ID of the root, and the communicator. You can also do the scatter. You can also do the scatter, that is the inverse operation of the previous command. you have an array and you want to share the information of this array between all your cores. In this case, you can use the scatter command, and the array will be automatically divided between the various cores. Clearly, if you reuse the same variable also for the output, you put information only in the first part of each array, and the other part of the array will remain empty. But in any case, this command could be very useful when you create on processor 0 your, for example, initial condition, and then you want to divide your initial conditional, your computational domain between all your cores. Clearly, this command could have some problem when, for example, the dimension of the array is a prime number. For example, in this case, how I can divide this this array in part with the same size? It is impossible. For this reason, exists some particular version of this function named scatter underscore v and gather underscore v that have the same syntax, but that allow you to divide your computational domain, your data, your array, in the most efficient way. For example, if I have as a prime number 17 and I have 4 processors, it divide it give 5 elements on the processor 0 and 4 elements to all the other, in order to minimizing the difference in size between the array in the output variable. And finally, it is also possible to share all the information contained in the various processors in a similar way, in a way similar to the gather operation, but giving the information not only to the root processor, but to all the processor. And the function that performs this kind of operation is the altogether function. The syntax is exactly the same of gather operation. The only difference is that here you haven't to declare the root processor clearly, because it is not necessary. And as I told you before, you have also the scatter v and gather v function. With this function you can perform most particular operation with scatter and gather. You can divide automatically your domain using the most efficient division you have, or with this function you can also decide the size of the block of data you have to send, and divide this block of data between the various cores with different size. The syntax of these two commands is a little bit more complicated, but in any case, as for all the MPI command, you can simply find all the data about the syntax and the usage of the function simply by typing the name of the command, for example, MPI underscore, sorry, MPI underscore scatter. Okay. This is for example for the MPI scatter, and this is the page of the MPI forum, the forum that create the standard. And here you can find the syntax of the function, a description of all the variable here, and the description of the operation that will be performed, and other link to similar function and so on. So please remember that you have some question about MPI, you can simply go on mpiforum.org and search the function you are interested in. Okay. Okay, it is also possible to perform some all-to-all communication. Until now, we performed only operation between one core to all the other. Now we want to perform an operation, for example, from all processor to all processor. For example, the MPI all-to-all function makes a redistribution of the content of each process in a way that each process knows the buffer of the other. You can imagine this operation like a sort of transposition of this sort of matrix. And it is clearly used for this reason in many cases. And finally, you can do also reduction operation that are operation as the all-to-all function. Also the reduction operation give you the possibility to communicate from all core to all core. This kind of operation permits us to collect data from each process, reduce the data to a single value, and you can choose to store the result of the operation you will perform only on the root process or on all process. We will see now what is this kind of operation you can perform. For example, this is the list of operations we can perform. Imagine that you have an array of elements, for example real, Imagine that this array was spread between a certain number of core. You can and imagine that you want to calculate the maximum value of the variable between all the core. If you want to perform this operation using, for example, point-to-point communication, you have to calculate the maximum value for each processor inside the memory of the processor. Then you have to send the information about the maximum from all the processor to processor 0, and then you have to calculate the maximum between the data that the processor 0 have collected. All these operations can be avoided using the MPI reduce command, using this particular option, MPI max. Using this command, the MPI library perform for you the operation that I told you. Clearly, I can also perform a lot of other operations. For example, I can do the minimum value, the sum of the variable that is contained on the array, the product, and also a lot of logical operation. Also the product, I have also and, bitwise and, okay. And for example, it is particularly useful MPI max lock and min lock that give you the information about the maximum value of an array and the location, that is the position inside the array and the ID of the processor that contain the maximum. Okay, and this is a very simple program that contain the use of the reduce operation. Clearly, here we are using the reduce operation, but we can change this command with the equivalent all-to-all command simply by writing MPI underscore all reduce. Using all reduce, the reduction operation will be performed at the same way, but the result will be available in all core included in the communicator you are using. So in this case, we have, as before, the header file, the declaration of variable, initialization, common size and common rank as usual, declaration of the variable, and in this case I have the input variable, the variable that contains the value, the result, the variable that will contain the result, the number of elements of the input array, the data type of the input array, the operation that I have to perform. In this case, I have to perform a sum, the ID of the root processor that have to collect the information, clearly the communicator, and the error variable. then at the end I can print from processor 0 the result simply with this if cycle. If my d equal to 0, then write my d 0, and the result for variable in the first element of the array and the variable in the second element of the array. And finally I have to finalize the environment. Clearly, as I told you before, if I put here MPI or reduce, the variable res will be created in all the process, and all the process have the same result. Okay. These commands clearly are very powerful. You can do a lot of things using this kind of command. This command have the advantage of hide the communication that you are performing. Clearly, the implementation of this collective depends on the implementation you are using. So, for example, on an Intel machine, this kind of function are particularly efficient. In other implementations, such as MPICH or OpenMPI, the efficiency is a little bit less. Clearly, since these operations are blocking operation and perform a lot of synchronization inside the instruction, they take a lot of time to be performed, especially if your data is big. So in some cases could be better to write your own collective by zero using point-to-point communication in order to use less time to do the computation. It was demonstrated that in large part of the current parallel MPI codes, about the 80% of time loss in data movement between cores is lost for collective communication. So I think that we can, before to start with the other part of the presentation, we can do some exercise about collectives. You can find at the same page of previous example also some example about collective. For example, here, 1 second. The exercise starting from exercise 7 are exercise on collective. And the first exercise, for example, is quite easy. In this exercise, the task 0 initialize a variable and then modify the variable, for example, calculating the square of the variable, and finally broadcast the value to all the other tasks. So I give you some minutes to do this exercise, and then after the break we will comment the other two exercises. Okay, I think that we can start again, and we can start commenting first of all some exercises. Particularly I want to comment with you exercise 7, and we can see directly the solution of the exercise. Come on. Okay, as before, the most important thing we have to include the MPI header file. Then we have to initialize the environment, call as usual MPI common rank and MPI common size. Then we have to initialize the variable on the first on the processor 0, that is the root processor in this case. Then we have to perform some operation on the variable, and then for the other processor, this is for processor 0, and this is for the other processor, we initialize and put to 0 all the value of the variable. Please remember that the initialization of the variable of your code depends on the implementation of the compiler that you are using. Generally, for example, GNU compiler do not initialize the variable, so you can find inside the variable some random values if the variable is not initialized. The Intel compiler usually initialize the variable to 0, but as I told you before, it is not automatic in a general compiler, so it is important that you initialize that you initialize your all your variable. Then after the initialization, you have to broadcast the value of this variable. As usual, this is the dimension of the variable, in this case only one element. This is the data type MPI int, and this is the root processor. Then we have to print the variable that we initialized, and finally we have to finalize our code, and it is quite easy. I think that now we can move to exercise 9. Here, the exercise, we will see the exercise for, if you want, at the end of the second part of the presentation, together with the final training session. In this exercise, we want to use the MPI reduce operation. Particularly in this exercise, each process initialize the one-dimensional array, giving to all the elements the value of the current rank plus 1. Then the root process, that is the task 0, perform 2 reduce operation in order to obtain the total sum of the value in this variable and the product of this value. Finally, each process to generate a random number, and the root processor, that is as before 0, have to find the maximum value of this between this random number and print this value. The solution, it is also in this case quite easy, particularly as before, and as I always say, we have to include as first step the header file. Without the header file, the program doesn't run. Then we have to initialize MPI environment and call MPI common rank and common size. And then we have to initialize the original array, putting in the array the ID putting the ID of processor plus 1, and then we have to perform the first reduction, that is a sum. As you can see, we have, this is the original array that is distributed between that is set to myID plus 1 for all the processor, and then we want to put the sum of the values of the array in a new variable named array final sum that have the same dimension of array. We have to give to the function also the number of elements contained in both in array and array final sum, the kind, the data type of the variable, the reduce operation that we want to perform, that is the sum, the root processor, and the communicator. Clearly, the result of this operation is that in this variable, only for processor 0, the values of each element of array final sum will be given by the sum of myID of all process. For example, if we have two processes, myID can be 0 and 1, so the array can have as value 1 and 2, and the sum of 1 and 2 is 3. So in array final sum, you have a sequence of n elements all equal to 3. And then for the next operation, we want to do the product, that is again this value for processor 0 multiplied for the value for processor 1, and so on. The syntax is also in this case the same, so you have exactly the same syntax, apart that for the operation we want to perform. In this case we have the product. Then we can write from processor 0 the results of this operation, obtaining the value that I told you before. The same also for the multiplication. Then we can also perform a random number generation, and in this case we have we can use the simplest random generator command that you have, that is srand for C, and this command requires a seed. We can use as a seed the ID of processor +1. For example, it is not mandatory, but remember that if you put here the same number for all the process, you obtain the same value of the random number for all the process. So you have to change the seed for all the process you want to use. Then you can use rand, and then you can print for each process the ID and the random number. And finally, using as before the MPI reduce operation, you can calculate the max value of the random number, of the random number. In this case it is quite easy. You have only to put here MPI max, and you will obtain on processor 0 inside this variable the value of the max of the random number that you generated in all the processors. Finally, for example, if you want to check how many times you used to do this program, you can call, for example, this subroutine MPI time that give you the machine time of the job, that is basically a sort of real number that at the beginning of the code is 0 and was incremented of, for example, the number of milliseconds that the code ran before to arrive to this command. It is the equivalent function of time, but used with MPI. The difference is that this time is synchronized, so the value of the time is the same between all cores. And then you have to put one of these instructions here and another one at the beginning of the code clearly. So then you have to do the difference between the two times, and finally print the time you obtain. And finally, as a last step, you have to call MPI finalize to close your program, to close the MPI library before to close the program. Now, finally, we can start with the last part of presentation, that is an introduction to MPI communicators and groups. As I told you this morning, usually almost all the code you can see will use only MPI common word. It is possible in any case to use other communicator, and you can create the communicator you want simply by typing some MPI command. First of all, we have to start telling that a communicator the communicator is a sort of link to a group of processors. So when we want to manage or to create a new communicator, we have before to create a group of processors. A group is in general a ordered set of processors and of process. Each process have to be associated with a rank, and the rank of continuous process the rank are contiguous for contiguous process, and they have to start from 0. Clearly, if you create a new group and link the group with a new communicator, you can perform also collective operation inside this subset of processes, and sorry. These groups are used mainly to specify which process should be used to cross-track a new communicator. So you can also use intracommunicator operation to communicate inside your new communicators, or intercommunicator to communicate between one communicator and another one. So, for example, an intracommunicator could be, for example, an MPI send. If you create a new subcommunicator and inside this communicator you perform an MPI send between two local processes of this communicator, you are performing an intracommunication. At the same time, if you have two different communicators and you want to pass an information, for example, one data from one communicator to another one, you can simply use another command to pass the information between the two communicators. And the most simple operation to do this could be, for example, using an MPI send, but on using MPI common word. In few words, you have two communicators, COM A and COM B. You perform some operation on COM A and COM B. Then you take from processor 0 on communicator A the information you want, and you can pass this information, for example, on processor 0 on communicator 2, simply knowing the ID of processor 0 on communicator 1 and 2 with the label, with the rank of MPI common word. Is it clear? Not much. Non abbiamo la lavagna. Okay. Okay. Imagine to have two communicators. Each communicator are associated to an index value for each process of communicator. Clearly, you have a given number of index. For example, imagine that you have 5 processors, 2 on communicator A, 3 on communicator B, and in total 5 process in MPI common word. Clearly, for example, you can take processor 0 and processor 1 of MPI Common World and say, this is communicator A. Then you can do the same for communicator B and say, this is the communicator the communicator B contains processor 2, 3, and 4 of MPI Common World. Then you have to create a set of new index for communicator A and B, and in this case, communicator A have the index 0 and 1 that are associated to 0 and 1 of MPI Common World. Communicator B have the index 0, 1, and 2 that are associated respectively to 3, 4, and 5, 2, 3, and 4 of communicator B, of MPI Common World. So if you know this correspondence, you can take the information from communicator 0 on MPI Common World and pass the information on processor 3, for example, that is on communicator B, and using this method you have the information you want passed from communicator A to communicator B. It is not simple, but it is the only method to pass the information. You can manage the group remembering that all group operations are local. The group are not initially associated with a communicator. You have to associate the group to the communicator by you. As I told you before, the group can be only used for passing some message within a communicator. You can perform a lot of operation on groups. Particularly, you can access a group, you can construct a group, you can destroy a group or a set of group. You can associate a group to a communicator and associate another group to another communicator. You can copy a group to another group. We can see this information in the following slides. First of all, you can create a group using the command MPI common group. And inside MPI common group command, you have to declare the first communicator that you have, that is MPI common world. When you create the new group, you can also create new communicator, and then if you want, if you desire, you can also create some other sub-communicator using as a root communicator the communicator that you create in the previous step. So you can create a nested set of communicator if you want. For example, you can create a new communicator using MPI concreate. You can determine the rank of the process in the new communicator using MPI common rank, but passing to MPI common rank the name of the new communicator. You can perform message passing operation inside the new communicator simply by using the same command as before, but using the new communicator instead of MPI common world. And at the end of your code if you want. It is an optional command, so if you want you can use it or not. You can free the memory of the communicator simply by use the command MPI common free and MPI group free. Now, imagine that you want to construct some communicator. I think that this is exactly the imagine that that I want to show you before. Imagine to have to have 8 processes. In this case, these are the process inside MPI common word. We want to create 2 new communicator. To create this new communicator, we have to create 2 new groups. The first group, for example, for the first 4 process, and the second group for the last 4 process. Then, when you create the group, you can associate the communicator to the group, and in any case you have to remember that in the communicator the ID of the process inside the communicator start from 0, so 0 corresponds to 0, 1 corresponds to 1, 2 corresponds to 2, 3 to 3. But in the second group, here we have to start from 0, but here we have processor 4 of MPI common word, so 4 is associated to 0, 5 to 6, 5 to 1, 6 usually 6 to 2, and 7 to 3. But in general, this is in general, if you use an automatic distribution. But if you want, you can also change the order. The only important thing is that inside the communicator, the process starts with 0 and ends with number of processes in the group minus 1. And in this case, for example, we do this. We attach to processor 4 the new label 0, to processor 5 2, to processor 6 1, and to processor 7 3.
Excuse me, I haven't understood well the meaning of the communication between the two.
No, this is only
just an example.
Just an example.
Oh, okay.
An example. So, MPI graphs, you have also some function that you can use to request information to the new group that you create. That this information, this subroutine, for example, MPI group size returns the number of processes that are in the group, and the MPI group rank give you the rank of the process inside the new group. For example, if we apply MPI group size to group 1, we obtain 4, as the same also for group 2. If we apply MPI group rank to group 1, we obtain, depending on the process, 0, 1, 2, or 3, and for group 2, we obtain 4, 5, 6, and 7. You can do several operations on the group you create. For example, you can, the first command, MPI common group returns the group associated with a given communicator. You can, for example, merge two groups throughout the MPI group union command simply by putting as argument the name of the first group, the name of the second group, the name of the merged group, and the error variable as usual. You can also do the intersection between two groups in order to obtain the intersection of, for example, group A and group B, that is the process that are both in group A and group B. For example, using the same example, we can also create a new group that contains processor 0, 1, 2, 3, 4, and 5, and processor and another group B, that contains 4, 5, 6, 7. In this case, processor 4 and 5 are both in group A and in group B, and using the in the group intersection as output, you obtain a new group that contains only processor 5 and processor 4. You can do also the difference between group A and group B. In this case, you obtain in new group all the process of group A that are not in group B. Or, and this is important, ordered as in group A. For example, coming back to the same example, imagine that group A is from 0 to 5. Group B is from 4 to 7. The difference between the two is a new group that contains 0, 1, 2, and 3. Ordered as I told you, 0, 1, 2, 3. Okay, you can also add some element in a group. For example, using MPI group include, you can create a new group that consists of all the process included in the group named group that have a rank that starts from 0 and arrives to start n-1. And we have an example. Imagine that we have a group that starts from A and arrives to J. Imagine that we want to create a new group of 5 elements, and with these ranks 0, 3, 8, 6, and 2, ordered following this order. We have to use this command, and using this command we will obtain a new group that include A as first element, D as second element, because here D is ranked as 3. 0, 1, 2, 3. The next element, 8. 4, 5, 6, 8. Sorry. 0, 1, 2, 3, 4, 5, 6, 8.
6, 7, 8.
Oh, sorry. I. Okay, this element. Then the same for G, that is 6 here. and finally 2, that is C in this case. Okay, you can also exclude some element from a group using the same structure with the command MPI group exclude. The syntax is exactly the same, and using this command you can exclude from this group the element 0, that is A, 3, that is D, 8, that is I, 6, G, and finally 2, that is C, obtaining the remnant part of elements that are this one, clearly ordered as this group. Communication management. The communication access operation are local, and they not require any inter-process communication. If you want to perform some intra-communication, we have to create an intra-communicators, or if we prefer, we have to use the MPI Common Work Communicator. So, communication, we can inquire the communicator with some command. Some of this command we already know some of this command. Particularly, we already know the first two, common size and common rank. Here, usually we put here MPI common work, but we can put here the name of the communicator that we want, and we can also use the function MPI compare that compare the two communicator, in this case communicator 1 and communicator 2, and give as a result this variable. The result have this value MPI ident if the two communicator are the same, congruent if the communicator are not the same, are different, but are associated to the same group. The same group attribute that contains both order and elements in the group. MPI similar if the two communicators have the same member but different rank order, and otherwise MPI unequal. You can use this environment variable of MPI, for example, to do some check on the result of the communicator's creation. Sorry. We can also, for example, this is the most important instruction to create a communicator. The first one is MPI com dump. This command simply create a new communicator different from the previous one, but that is identical for number of element, position of the element, and process to the first communicator. The syntax is easy. This is the original sorry. This is the original communicator. Sorry. Okay. This is the original communicator and this is the new communicator. And if you want to create a new communicator starting from a group that you have already created with MPI group create, you can use this command mpi-com create that needs of the original communicator, in the simplest case MPI common world. The name of the group, the name of the new communicator you want to create, and error variable. Sorry. Okay. A practical example. First of all, in a program in which we want to create a new communicator, we have to declare MPI common rank, MPI common size, for example, for the original communicator, that is usually MPI common world, and this is the first step. Second step, we have to use MPI common group to create a new group named work group. Then we can define something. We can exclude, for example, some element from the work group, for example, using MPI common group exclude. And finally, we use the new group that we create to create the new communicator simply by putting here MPI common world, that is the global communicator that we use here, here, and here. The name of the new group, the name of the communicator that we create here, new group, yes, the name of the group that we create here, and finally the error variable. Okay. We can also perform some strange operation with communicator. For example, we can associate particular values to the communicator. For example, using MPI using MPI common split, and in this case you can associate, for example, as many new group and communicator as there are distinct values of colors. We can intend colors in a large way. I will show you with an example what means color for us. We can also rank with this command the new group using the colors, and this is a typical example of the use of colors. For example, we can imagine that we want to create a 2D topology inside the group that we have. For example, we can start with MPI common world, for example, using MPI common split. Then we can set a logical row number for each process in MPI common world with the command with this instruction, and the ID in the column using this other command. Then we can create a new communicator calling MPI common should be equal to MPI common word, then we can use the command MPI common split to split the communicator in column and row, and using this command, for example, we can associate a different index to the original communicator, to the rank of the original communicator, that is this one, and this new rank here. But usually this is not used because there are better methods to create a 2D topology in MPI, but this method is presented in a more advanced course, probably only in the last part of our school on parallel computing, or in the winter school, on the advanced winter school of parallel computing that I think that will be in February. Okay, at the end of the program, when you want to leave the program before to do MPI finalize, you can also free the memory of the group simply by using MPI group free and MPI com free. And as I told, as I told you before, you can also create some intracommunicator, for example, coming back to the same example that we see before. We have two groups and two new communicators here. We want to pass a message from here to here. The method that I told you before consists in using MPI common word and passing a message from 0 to, that is here, to 4, but using an MPI common word. But I can also create a specific communicator that contains only 0 and 4. We can call this communicator, for example, communicator A, and I can pass the information from processor 0 of communicator 1 to processor 0 of communicator 2 simply by performing a send-receive operation between processor 0 and processor 1 of the new communicator A. And I think that that's it for this presentation, and now we can finish the tutorial simply by finishing the tutorial that we have in the list here. So the last 45 minutes, you can use the last 45 minutes of the course to do the other exercise that you find here. Please remember that with the knowledge you have, you can arrive only to here. In order to solve also this other exercise, you need to know the other information that are included in the course on parallel computing that we do at Cineca, and that lasts for what concerns simply 3 days. In any case, it is useful see also the exercise 16 because it is the most complete exercise and it use a lot of very useful instruction. Even if you don't know some command, it could be useful to understand this command after you have seen the presentation of the parallel course of Meccanica. In any case, in order to write a code that use both MPI and OpenMP, the instruction that you have, the instruction that I show you today are sufficient. So you can also use this instruction to write your first hybrid code that use both MPI and OpenMP. In any case, if you want to see a program that use both MPI and OpenMP, you can see the
Second one.
Debugging it. Sorry. Okay. Yeah. Okay. These are exercises. I think that these exercises are really useful because you start from this simply serial code. Simple. Okay. And starting from this, you perform both MPI and OpenMP operation, and to obtain a very optimized version of your code. And that's it. If you have question, you can ask.